Good afternoon, everybody. Welcome to Taco Tuesday. We look forward to these every month, every week. This is the first in April, and it's focused a little bit on commercial topics. So today's presentation is HVAC components of a hydronic heating system. Rich Medairos will be the main presenter, and my name is Brett Zerba. Most of you, I recognize quite a few of the names. Most of you have been through this before, so you know who we are, so we don't give you too much introduction. But before we get started, can a couple of you wave your hands if you that you can hear me and see Rich's screen? Let's see. Okay, good. I see some people. Hold on, I don't see many people hand waving. Oh, there's somebody. Thank you. Oh, good. Shauna waved. So that's good. That's good. We got some highs coming in too, so I think we're all set there. As has been in the past since the pandemic started, and we started these Taco Tuesdays over the webinar, you will receive an email tomorrow, about 24 hours after today's presentation, with a link to the recording if you'd like to view it again, as well as access to your PDH certificate. So if you need that requirement and your state accepts it, it is available for you. It's a PDF download. And again, if anyone has any problems, just send the send an email to the site, and we will make sure we get you a copy. TACO again celebrating our 101st year. Imagine that, 101st year of existence. Johnny White is the current owner. It's a privately held company located in Cranston, Rhode Island, and he's third generation. And his two boys are both married, and they both work at the company. And exciting times for both families. So that's those are great. Those are great. Let's see. Rich Medairos is very, very knowledgeable, as most of you know, in HVAC hydronics, HVAC system designs. He's been in the industry more than a few years. So please ask the questions. I will be monitoring the questions and make sure you get them. So we'll get to as many as we can, and as in the past, we'll answer some offline if we have to. But all you folks always ask great questions, and it really does help the presentation take off and do a nice job. So keep up the good work. Pat yourself on the back. Keep up the good work. As spring comes around the corner here, you know, let's hope 2021, as we get into summer and the end of spring, gets a little more momentum than 2020. So let's just hope that happens. And I have a good feeling that it's gonna. So let's go from there. We are recording this. There are no handouts for today's presentation. So if you do need, if you want to review it, you got to get a copy of the recording. So please beware of that. But you know what? I'm done talking. You folks are sick of hearing me as usual, but I will be monitoring the questions, so please ask away. And Rich Medairos, take it away.
Well, thanks, Brett, for that introduction. Good afternoon, everyone, and welcome to Taco Tuesday. Today's topic is HVAC components of a hydronic heating system. Just a quick introduction about myself. I am a mechanical engineer specialized in the engineering and design of HVAC systems. I've been in the industry for several years. I am a PE, professional engineer, registered in a couple of different states. So that's my background. So let's get right into today's discussion. So the things that we're going to cover in today's discussion, I always like to put this this kind of warning up there. You're going to see different diagrams, and the diagrams are specifically for our use in training. And so we always put a little note in there that our diagrams are not for construction. We also want to put a statement up front that anybody that's doing this type of work, design work, should review and comply with all local and national codes before starting a hydronic heating system design. So just a little reminder. So what are we going to cover today? Well, we're going to say what is a hydronic heating system, equipment that goes into a hydronic heating system, how does everything fit together, where does everything go, proper location of equipment, and then questions at the end. So I like to start off with a very simple definition and say, what is a hydronic heating system? Well, a hydronic heating system is a system that utilizes a hydronic fluid, in our case, water or water glycol solutions, to transport heat from its source, usually from the heating plant, to its destination. I have a little pictorial here. Excuse me one second. A little pictorial here to kind of indicate that we're going to go from our source, which in this case is a boiler, to an ultimate destination. And we'll get back into these different items, but to the item that's on the right, which is called an active chill beam. And you'll notice, let me see if I can grab my pen here. You'll notice that the active chill beam has pipe connections. So to oversimplify things, and I'm going to show you a real diagram a little bit later, but there would be piping exiting the boiler and finding its way to one of these pipe connections, and that would be the source and the destination, and then the return piping would come back and connect back to the boiler on this general idea here. Don't worry so much about this diagram. We're going to get into the real diagrams in a few minutes. Okay. So with that in mind, let's talk a little bit about equipment that goes into a hydronic heating system. Now, most of this equipment you should be familiar with. So let's just go through the list, and then we'll take a look at some actual component pictures. So we have the piping system, which includes valves and fittings. We have boilers. In our case, we have TACO pumps, TACO expansion tanks, TACO air and dirt separators, and air handling units, terminal units, and we also have controls. So these are the major components that go into a hydronic heating system. So let's take a closer look at each one of these. So the first one is a piping system, which includes valves and fittings. And what I have shown here on the left in this photograph is a sample of some black iron, or sometimes referred to as carbon steel pipe. And then also another photograph here of the different fittings that you can run into: elbows, reduces, T's. You can see all of that. And for today's discussion, I've just shown you one type of pipe material for a metallic, but it could be, in this case, it's carbon steel, but it could be stainless steel, a variety of different materials that are available, could be copper in the metallic category. So I'm just demonstrating the types of components that would fall into the metallic category. And then on the right side, we have Schedule 40 PVC pipe. And in this case, again, I'm just demonstrating a general category of plastic pipe. There are all kinds of materials out there in the industry today. There is PEX tubing, polyethylene cross-link, PVC, as we've shown here, is a variety of different materials. So the type of material that you ultimately select for your system will be based on a variety of variables: the cost of the material, the temperatures, the pressures, and whether or not it's compatible with the fluid that you're using. Since we're talking mostly HVAC systems, the majority of materials that are available are usually compatible with HVAC systems, because for the most part, HVAC systems use either water or water glycol solutions as the working fluid. Okay, the next category would be boilers.
Hey, Rich, we have a couple questions associated with the piping.
Oh, great.
Yeah, the first one, which is really a very good basic question. Do you see many systems where you combine different types of material?
Yeah, in fact, we do. In our headquarters building, we're using a combination of welded steel, which carbon steel, copper, and we're also using plastic material in our building. So yeah, we have a full range in our headquarters building. And in most projects today, they do use multiple materials for the buildings.
Awesome.
A lot of mechanical systems for pipe sizes that are smaller than I think it's 2-inch. A lot of people will use copper up to 2-inch, and then they'll use carbon steel above 2-inch. But PEX tubing is very popular these days. Variety of different plastic materials are also very, very popular.
Then there's a second question that I've never, and this is, anyways, is it correct that in a heating system you do not use galvanized steel?
That's an excellent question. I'm going to have to make a note of that and see if I can come
Okay.
up with an answer. I've never been asked that question before, to be honest with you. I don't remember seeing galvanized steel pipe in an HVAC system. I've seen it in potable water systems, but I haven't seen it in an HVAC system. So yeah, that's a great question. Let's see if we can do a little research on that.
All right, we'll try to do some research on that one for him.
Yeah,
Great
sounds
question.
good. Is that all we have for now, Brett?
Yep, yep.
Okay, so the next group of components would be boilers, and I have on the left side a photograph of condensing boilers, and there are a variety of manufacturers out there. So we recommend that you contact your TACO rep. Most of our TACO reps also carry different manufacturers of boilers, and they can help you decide what the right combination, what type of boiler and combination of boilers that you should have for your heating system. But the two major categories are condensing boilers, which is on the left, and non-condensing boilers. And the one on the right is a fire tube boiler. Fire tube boilers have been around for a very, very long period of time. And for the longest time, they were sort of the workhorse for large commercial projects. I know that going back probably about 40 years ago, nearly all of our projects that were of any reasonable size used fire tube boilers. But today, there's a whole series of boilers that are available. So check with your TACO rep. They generally carry boilers along with TACO equipment, and they can guide you through which is the right boiler for your particular project. Okay, so the next component category are pumps. And of course, the pumps we're talking about are TACO pumps. The one on the left is called a base-mounted end suction pump. It's probably the most popular pump in the industry today. We manufacture more base-mounted end suction pumps than any other category of pumps. You can also get an end suction pump in what is known as a close coupled, but I wanted to show you a photograph of the most popular for the base-mounted. Base-mounted pumps have a motor indicated on the left here. I grab my pen so I can show you what that's all about. So here's the motor over here, and then here is the pump. Now what you can't see, because it's covered by this cover guard here, is there are two shafts, one associated with the motor, so I'm going to kind of make a little shaft over here at the top. There is the motor shaft, and then there is the pump shaft, and those two shafts have to be aligned with each other to within 5/1000ths of an inch. And to make the connection, there's a coupling that goes between the two. Brett has a great presentation that he does, which shows the fundamentals of pumps, and he goes into the detail of how these couplings work and the concept of the shafts and stuff. The important thing to keep in mind is that a base-mounted pump, regardless of what style it is, does need to be field aligned, and it has to be done within 5/1000ths of an inch in terms of the alignment. The second major category of pumps is probably the fastest growing category, are called vertical inline pumps. And the one that we've shown here in this photograph on the right is called a split coupled pump. Now you can't really tell unless I point it out to you, but we have a similar situation where we have a motor shaft. In this case, the motor is oriented vertically, and then we have a pump shaft. And then those two shafts are connected through a machined coupling. So the coupling for the end suction pump is a flexible coupling, but because the motor, in this case here, and the adapter and the pump all are connected through what we refer to as machine fit. So there's no physical alignment that's required. So we do not need to have a flex coupling. So we have this split couple right inside here. And it's made out of billet aluminum. And that connects the motor shaft to the pump shaft. Any questions about these two styles of pumps? They're probably the most popular for hydronic components.
There is a good question. Would you recommend any mechanical seal difference between a chilled water or a hot water pump?
In general, for the temperatures and pressures that we typically run for HVAC systems, the seals are the same for both chilled water and hot water. We can provide high temperature hot water, let me rephrase that. We can provide seals that are designed for high temperature hot water systems. So yes, there are some variations for those components.
Awesome.
Any other questions?
No, good shape.
Okay, so let's go on to a couple of the different style pumps. We get into larger pumps. Typically, the larger pumps wind up being either, in this case, horizontal split case. This is called a GT series horizontal split case, and I believe these go up to somewhere around 15,000 gallons per minute. And then we have the TC style pump, and you can kind of think of TC as top connection. And this is called a vertical split case pump. So let's go back to the horizontal split case. The actual casing of the pump, I kind of draw a line here. It's not going to be the best line, but it's split along this horizontal plane right there. And so to dismantle the pump, you unbolt these bolts. You can barely see them in this photograph, but they're there at the top, and you lift off the top half of the pump. And that allows you to service the impeller, the bearings, the shaft, and so on. One of the nice features, and this is true of all Taco pumps, if I didn't make that known, let's go back here. Erase here, and then go back. Whoops, sorry about that. Let me hang up that phone.
The bat phone.
Yeah, why is it that the bat phone always rings when we're doing a presentation, Brett?
Typical.
Typical. Yeah, so the one on the left is a horizontal split case. The one on the right is a vertical split case. You can see the bolts around the perimeter here. And so if I kind of think of, if I'm drawing a vertical line, that entire front of the pump comes off in this direction. That allows you to service the pump. So whether it is let's see, go back here. Whether it's a horizontal split case, a vertical split case, let's go back to the previous one, an end suction pump or vertical inline, all of the Taco pumps allow you to keep the pump connected to the piping system if you have to service the pump. You do not have to disconnect the pump from the piping system in order to dismantle the pump and take the internal components out. And that's a major benefit if you're servicing any one of these pumps. Okay, the next component that's required in a system would include, on the left side here, I have full acceptance bladder style expansion tanks. And this is probably the most common expansion tank in the industry today. We probably provide more of this style expansion tank than any other expansion tank in our lineup. So expansion tanks are very popular. Full acceptance means that the bladder can expand to the full volume of the steel container. So for example, if I just arbitrarily, let's say this expansion tank up here that I'm pointing to is 200 gallons, the bladder that's inside that expansion tank, if it fills up with water, can expand to the full 200 gallons of the steel container. That's what we mean by full acceptance. We also manufacture partial acceptance where the bladder is a little bit smaller than the steel container. They're a little bit less expensive. And then I also wanted to show everyone, even though today we're not talking specifically about potable water systems, I wanted to show you that we make a full line, including these small, we call them micro tanks, for potable water systems. So these are expansion tanks on the right are for potable water, bladder style tanks. And then the ones on the left are full acceptance bladder style tanks. The ones on the left would not be suitable for potable water. The ones on the right would be suitable for potable water. And you can see the one on the right there, NSF certified. Okay, so those are some more of the components that go into an HVAC system. Let's continue. Now we also get into the category of air and dirt separators. So grab my pen again. So the two on the left, these two are identical. It's just that I have one fully assembled, and then the second one is where the top, you can show how the top can be disconnected. There are bolts. You can see the bolts here on the first one. I can point to the bolts. And this is called a 4900 microbubble air and dirt separator. And it has a basket, as you can tell from the exploded view here, that is filled with Paul rings. And those Paul rings allow the water to, or the fluid, let's use the term fluid, to change direction thousands, perhaps even millions of times, and allows the air to be extracted from the water. And very, very tiny. That's why we call them micro bubble, because it's the size of just a few microns. So we can get the nearly all of the air out using this type of device. So this is the micro bubble is probably the most popular that we provide out there. It's the one that does the best job. And as you can see, again, think of the piping system as being fixed. In this case, let's say the pipe, it's connected to the piping system. You can take the top of the one on here off, and you can remove the basket, and you can pressure wash the Paul rings that are inside the basket and then put it back together. So it's very easy to service this type of air and dirt separator. The second category of air and dirt separators are called inline air and dirt separators. And if you look down from the top, I'm going to kind of draw a gross circle here. If you look down from the top, you would see the connections are along the, let's see, would be in line with the center of the circle. So there's the connection on the left, there's the connection on the right, and you can kind of think of that. If I draw a line through each of the connections, it goes through, sorry, that line's not the best, straightest line in the world, do it again, and that becomes an inline. So that's why we call these inline air and dirt separators. The only difference, so there's a couple of differences. The one on the left is a flange connection. The one on the right is a grooved pipe connection, which would be similar to Victaulic. And the one on the left also has an auxiliary strainer in here. You can get those strainers for the Victaulic too, but I wanted to show that you can get them in both different ways. And then the third category of air and dirt separators is called a tangential. I always have difficulty pronouncing this word. And the tangential, so the fluid flow is tangent. The connection is tangent to the connector here, or to the body of the air and dirt separator. And these were very popular. People still use them today. The fluid enters in this direction and it swirls around this way and then eventually finds its way out. And one of the things that's important to recognize for this type of air and dirt separator, they work best for constant flow systems that have a fixed flow, so many gallons per minute without a variation. Because in order to get this vortex to work properly, you have to have a certain velocity. And as the velocity drops off, the vortex begins to diminish and the effectiveness of the air and dirt separator begins to drop. And again, this particular one here has a strainer, so which is an optional component. The one on the right is shown without the strainer. Now, the main advantage to the one way over here on the left, the Taco 4900 microbubble air and dirt, it doesn't matter what the flow is. So for variable flow systems, which most systems today certainly when we're talking this topic today of hot water heating systems or hydronic heating, there are variable flow systems, either primary, secondary flow systems or variable primary flow. And these air and dirt separators work well, whether it's at full flow or some percentage of full flow. So perhaps, 20% of the full flow, that sort of thing. But the ones on the way extreme on the right here become less effective as the velocity drops off because you can't maintain that vortex of the spinning to get the air and dirt to fall out. Any questions about air and dirt separators and the different styles and the types?
Actually, we have a couple of great questions. Is there any danger from oversizing an expansion tank?
Oh, that's on the previous slide?
No, is there? I'm sorry. No, I maybe I misspoke. Is from an engineering standpoint, is it okay to oversize expansion tanks?
Yes, on the previous discussion where we talked about expansion tanks, there is no detrimental effect to the operating characteristics of a hydronic system if the expansion tank is larger than what it needs to be. If you make the expansion tank larger, the only real penalty is the cost of the expansion tank. You'll be paying more money for a larger tank and the amount of physical space or real estate that the tank will take up. So there's no operational penalty, but there is a space and cost penalty.
So we have a great little comment here, Rich. So far, you've talked about, well, I know you've talked about pipe and fittings and whatnot, but the main components, you talked about a boiler, you talked about pumps, you talked about expansion tanks, and you start air and dirt separators. Can somebody's saying he thinks there's a lot of young folks on engineers. What does each component do?
Oh, that's a great question. So maybe the simplest thing is to just kind of walk back. So the piping system is the conduit by which the fluid flows throughout the system. We'll say that. That's what they're responsible for. The boilers are responsible for heating up the fluid. The pumps are responsible for moving the fluid from the source, which in this case would be the boilers, to the terminal devices. The expansion tanks are responsible for, since the fluids that we're talking about in HVAC systems are basically water or water glycol solutions that are considered to be incompressible fluids, which means that as the temperature increases, the fluids will expand, and if they have no place to go, which is what the purpose of an expansion tank is, if they have no place to go, then it will break the equipment or the piping system. And it's one of these things, don't try this at home, but if an expansion tank is isolated from the system and the fluid heats up, if the safety relief valve should fail, then the expanding fluid will break something in the system, either the pump, the pipe, or the equipment that's in the system. And then the air and dirt separators are designed specifically to remove the particles. So a piping system over time does generate deterioration. The material will find its way into pumps and chillers and boilers and stuff like that. So we want to remove that material. Excuse me one second. We want to remove that material before it damages the system. So that's the purpose of getting rid of the dirt. As far as getting rid of air, air is the enemy. When you fill a piping system, even if you fill it to the very, very top, and there doesn't seem to be any room, there is air in solution. So the water or the water glycol actually has air trapped in solution. And over time, that air will come out of solution. So you want to remove it from the system. And that's the main purpose of an air separator. So hopefully I've covered the majority of the operations.
Excellent.
Where we've covered so far. Okay, so now let's talk about where does that heated fluid go? Well, it could go to an air handling unit, and this is a very simple indication of an air handling unit. There's in this section of the air handling unit, excuse me, there would be, I'm sorry, losing my voice here today. That's not good, Brett. in this section here, this is where you would connect the ducts, either through the back, as this could be the outside air, this could be the return air. Let's say I'll label this return air, this could be the outside air. And then it passes through, the air goes and passes through a series of filters and then through these hydronic heating coils. And that's where our piping system, again, and you're going to see this in more detail in a minute. So we might have a supply pipe that goes in this, fluids flowing in this direction, and a return pipe, fluid flowing in this direction. And so that's very simple. As an air handling unit, hydronic air handling units usually have heating coils. We sometimes just label them as HC for heating coils. This one has a combination of heating coil and cooling coil, but I'm most interested today, since we're talking about hydronic heating, the heating coil. Okay, and then we start getting into the details a little bit more on the terminal components that you find. So one category is called fan coils. They come in a variety of shapes and sizes, and typically they have a finned tube coil, which you can see here, and they typically have a fan, which is where the name fan and coil or fan coil comes from. And again, you have these piping connections. So let's kind of just indicate, here are a couple of piping connections. There's one there and there's one there. And so the hot fluid would flow into the coil through the piping connections. And for our discussion today, by the way, we're going to assume that our supply water temperature is 180 degrees and our return water temperature is 160 degrees Fahrenheit. So this would not be a condensing system, because generally speaking, for condensing systems, in order for the boiler to operate in its condensing mode, you have to have return water temperatures that are below 130 degrees Fahrenheit. The next category of terminal unit is fin tube radiation. It's probably the most popular type of radiation that's out there. As the name implies, the first two words here, fin tube, there is the tube right there. And generally speaking, the tubes are usually copper, and the fins themselves are mechanical or press fit onto the tube, and the fins are usually aluminum. And then it's covered by a metal cover. This particular one has a damper that's inside. You can't actually see the damper, but it's controlled by a manual knob here. So as I turn that knob, the damper opens and closes. That's terminal devices, that first two categories, fan coils and fin tube radiation. There are other components. So let's go to the next category here. I also have an active chill beam. And again, excuse me one second. An active chill beam, and you can see the connections here. This happens to be what is known as a 4-pipe active chill beam, where we have both hot water and chilled water connections. But since we're talking about heating systems, we'll just think of this pipe here going in. Maybe that's going in on that side, and the return water is coming out on this side here. So that's where our piping system would be connected to an active chill beam. That's what we got down here. Another terminal device is called a hydronic radiant heating panel. And these two are the same panel, by the way. This one is we're looking at the back side without the insulation installed yet. And there's the piping connections, there's the supply, and then there's the return piping connection. And this is just the same device, only flipped up on its side so you could see. This would be the ceiling side, even though it's in the vertical position. You kind of use your imagination that's, so we're actually seeing the underside. If I can kind of point to this, that would be the underside here. That's what it looks like. And these are designed to blend in with ceiling types. In other words, some manufacturers will actually paint them to look like a ceiling panel, like a 2-foot by 4-foot ceiling panel, or a 2-foot by 6-foot. 2x4 is probably the most common size. I've designed lots of systems using these hydronic radiant heating panels. They're quite popular in the Northeast. Okay. Any questions about any of these terminal devices that we've covered so far, Brett?
Actually, we do. What do you mean by return air?
Oh, you mean on the air handling unit?
Yeah.
Yeah, okay. That's a good question. Let me see if I can. I'm going to try pulling up my whiteboard here for a moment. Let's see if I can get that to work. There's my whiteboard, and I'm going to move my whiteboard out of the way here. So if I look at an air handling unit, I'm just going to make a very, let's say I make a room, and we have a happy person standing in this room. It looks a little bit like you, Brett.
Yeah, well, smiling, that's the key.
Smiling, yeah. So if we had an air handling unit, let's say that, let's just make a box. The simplest air handling unit in the world is a box. And let's say that we had a return air grill in the ceiling, and the return air goes into the air handling unit. So I'll call this the air handling unit up here, AHU. And we generally have, so that's the return air. That's what we label as the return air. And then for the person, the happy person in this room to breathe, we have to have a little outside air. So we're going to bring in some outside air, usually through louvers on the air handling unit, and then usually some kind of filter media so that we clean up the outside air. So label that outside air. And those two mix together. And let's say, again, we're talking about heating today. So let's assume that the outside air temperature was 5 degrees Fahrenheit. And then we have a filter. So I'll just put an F in here for filter. I'll put a filter right there. And then these two air streams mix. The outside air mixes with the return air, and then it passes over a heating coil. Like I said before, we call that a heating coil. And then we'll have a fan in here, and it'll be the grossest fan you ever saw. Put a F for fan. Then we have some more ductwork, and that ductwork finds its way into the room here. And then that becomes the supply air. So we call this the supply air here. SA, supply air. That's not the best S in the world, but so we have our supply air, which comes into the room from the air handling unit. The return air mixes with the outside air, passes over the heating coil, and gets blown through the ductwork into the room itself. So hopefully that kind of answered that question.
Yep, great answer.
Good
I like the
stuff.
whiteboard. I like the whiteboard.
I do too. The whiteboard's very handy. Okay, so we talked a minute ago about, let's go back here one slide. We talked a second ago about some more terminal units, which includes active chill beams, in this case, hydronic radiant heating. And then the last major component that you need to have for a heating system is you need controls. And I'm displaying here the control system that Taco offers, and it's called the Clarity Cubed, I think is our actual name. I like to refer to it as Clarity 3. It's easier for me to say the word than cubed. It's actually, if you look on the name of the controller itself, maybe you can barely see it in this picture, so I'm going to try pointing to it here. But the name Clarity, and then at the end of the Y, there's a cube, you know, right there. So it's actually called Clarity Cube, but I like to call it Clarity 3 just to make it easy for me. And so there's a whole series of different controllers that can be utilized to control a hydronic heating system. So I've covered the components for a hydronic heating system and talked a little bit about their purpose. So let's put all of this together and do a very simple design for a hydronic heating system. Before I move on, any questions about anything we've seen so far, Brett?
No, keep going.
Okay. So let's talk a little bit about, let's say I want to design a heating system, but where do I start? And I always like to say I started with a building. And in this case, we are going to have a simple office building. We are going to pretend that this building is 500,000 square feet and that the length and width, it's a simple rectangular building, is 500 by 200. And if you do the arithmetic out, you'll find that that is equal to 100,000 square feet. So 500 by 200. The footprint of the building would be 100,000 square foot. So each floor of the building would be 100,000 square feet. And our building is going to have 5 floors in it. So we multiply 5 times 100,000, and that's how we come up with 500,000. So that's the size of our building. All right, and so we're also going to have 10 zones per floor. So each floor of the building is going to have 10 terminal devices, and we have 10 devices per floor times 5 floors. We're going to have 50 terminal devices, and you'll see what that looks like in a minute. The next thing I have to decide is I have a separate presentation, which I'm not going to go into today, on how to design a central heating plant. But when it comes to design a hydronic heating system, we do have to give some consideration to the fuel source. But in our case, let's talk about the load first. So the building size is 500,000 square feet, and I'm using an estimate of 30 BTUs per hour per square foot, which for the Northeast is a reasonable number. Depending on where you are in the country, the number would be the higher if you're in a colder climate or less if you're in a warmer climate. So that means the heating load is estimated at 15 million BTUs per hour. That's simply 30 BTUs per hour per square foot times 500,000 square feet. And I have an asterisk here because I always like to make the note, actual heating load should be based on a detailed heating load calculation. And you can use the TACO load tool, which we have a second at the end. I'll show you how to download that for free. And then in our system, it does not include domestic hot water. So we're just allocating 30 BTUs per hour per square foot for space heating. We're not doing any domestic hot water heating. So that's just a quick estimate of what the size of our capacity of our system needs to be for this imaginary building. And I have a link in here since Brett is recording this. If someone wants to take this down in the future or today, it's tacocomfort.com/software. And that'll take you directly to the software that you can download, our load tool, if you want to use that for heating and cooling load calculations. And our load tool is based on the ASHRAE method. It's a very simple, easy way of determining building loads. Okay, so the next thing I always like to talk about is the type of fuel. For today's discussion, I'm not going to go into the analysis of fuels. I'm just going to say that we're going to make sure that we have what the availability of the fuel is, the cost, the heating value. That goes into deciding what fuel you ultimately going to need for your facility. And obviously, if you have something like fuel oil in lieu of natural gas, you have to have some way of storing that. So you need storage systems. So for today's discussion, I'm just going to use natural gas. Okay, any questions about where we are right now, Brett?
Oh, good shape.
All right, so let's go into an actual system. Now, the first diagram I'm going to show you is almost impossible to read, but this is a hydronic heating system, complete design. We have 10 terminal devices per floor. We have 5 floors, you can see. So we have a total of 50 terminal devices. We have 3 boilers and pumps. And now I'm going to zoom in on the next slide so we can look at each of the components to see how they're arranged and what order they happen to be in. But I wanted to show you a picture of the overall system first. So let's zoom in now and look at just the boiler plant. So here we have 3 boilers, and I have made somewhat of an arbitrary decision. I can tell you my logic in a minute. Where each boiler is sized at 50% capacity, which means I have redundancy. That means that if at any moment in terms of its operating, I could lose a boiler, and if I had my peak heating load, I would still have 100% capacity. In this piping system, my boilers are on the left side here. I'm going to circle this. All of this piping over here is on the left side of the hydraulic separator. And let me point out what the hydraulic separator, there it is right there. And so this is called the primary pumping circuit. That's the primary side of the system. And everything on the right-hand side of the hydraulic separator, and let's say I go down and I pick up all of those things which I showed you a minute ago, all of those different terminal devices. And I come all the way back here. I'm picking up all of this piping and find my way back. So this is the secondary side of the system. Primary is generally associated with the generating equipment, since this is heat generating equipment. That's called the primary side, and then the secondary side. The secondary and primary side are separated by a hydraulic separator. Now, this is not a heat exchanger. If I was a molecule of water, I could pass through the hydraulic separator from one side to the other. All right, so now let's look at some of the components more carefully and see what we've got here. So on the primary side, let's just look at one boiler at a time. Now, again, as I have down here, it says this is not for construction. The intent is not to show every single device in the system, but to kind of give you a general idea of what the arrangement should be. So in this case, we're pumping away from the boiler. Depending on your philosophy, some people like to pump to the boilers. I like to pump away from the boiler. The main reason for that is that if I pump away from the boiler, then I can maintain a reasonable pressure inside my boiler. And also, I want to try to get the hottest water on the suction side of my pump if I can. And then if I go to the second, well, let me just go through that. And I also have, for balancing purposes, in this particular design, by the way, it's a constant flow on the primary side. In other words, I never change the flow. In this case, roughly 769 gallons per minute. And as long as that boiler is operational and that pump is running, it's going to run at a constant flow for the primary side. And the circuit for the primary side is down here into the hydraulic separator, comes back out, goes into the individual boilers as it flows back in each case. Comes down here. And then it goes, feeds back. There's one boiler, then picks up these second boiler, there's two boilers, and then when it comes back here, we have all three boilers going into the hydraulic separator. So the multi-purpose valve does three functions. It's a check valve. It's also an isolation valve. You can use it to shut off the flow, and it's also a balancing valve, so you can use it to balance. So especially in a constant flow system like this, you're basically going to turn the valve to get the exact flow that you're looking for, in this case, roughly 770 gallons per minute. So those are all the components. Not every component, like I said, is shown here. There is an isolation valve shown on the boiler. On the discharge side of the boiler, we typically would have another valve on the suction side of the boiler, so you could isolate and service the boiler, those kinds of things like that. And then on the secondary side, so over here is the secondary side, we have the air and dirt separator, in which case I would recommend the 4900 series with the microbubble Paul rings. We also have the expansion tank over here. And then we have the secondary pumps. And similar to the primary side of the system, again, this is the secondary side, these pumps are manifolded together. And because they're manifolded, these are variable speed pumps. So depending on the demand of the system, I could run any combination of these. But in general, since I've sized them for 50%, I would only run two pumps at a time, perhaps this pump and this pump initially, and then this third pump here would be my standby. If I should lose any one of these pumps, then my standby pump would become operational, so I would never lose capacity in the system. So that gives you a quick snapshot of all of the components on the main mechanical room or boiler room side of the system. Any question about the relationship of each one of these components and what we did cover their function previously, but how they operate. Let me get rid of some of these lines. So it doesn't look
a couple of questions / comments. Can you clarify that HS-1 is not a heat exchanger?
That's correct. This is called a hydraulic separator that we've shown here. So a hydraulic separator is a pre-engineered device that creates a bridge between the primary loop and the secondary loop. So if I was to draw just a piping system, this hydraulic separator takes the place of a piping system. So in other words, my primary piping might look like this, and there's my supply and my return on the primary side, and then I would come off here for the secondary side and then return back on the secondary side. So here on the left is the primary, and here on the right is the secondary. So that's if you did it with T's and pipes and so on and so forth. So this guy right here takes the place of all of this piping. So if I kind of put a rectangle around it, you get a general idea of how this thing works. And that's called a hydraulic separator. And it creates a bridge or separation between the primary and the secondary loop. Does that help?
Yep. One other question. Is this software that the picture that you drew or the design you drew, is that available for just TACO reps, or is it available for everybody?
It's available for everyone. And I think we're going to have a few minutes at the end here that I can show everyone how to download this software, both the load tool and the piping system, which is called Hydronic. Say the words for me, Brett. It's the
HSS, Hydronic System Solution.
That's it, Hydronic System Solution, HSS software. And
Yep.
Brett is actually an expert in this software. And I don't know if we've done the HSS presentation for TACO Tuesday.
It's been a while.
Been a while. Do we plan another one this year, or is that going to be next year?
We could. We're only through June. We don't know yet.
Yeah, that's true. Yeah, if it's a return for popular demand. Okay, so that's the boiler plant. Let's take a little bit closer look now at the terminal device. So in this case, we have two terminal devices. Each one is 300,000 BTUs per hour. And down here, we can see the supply piping that came from the vertical main. So there's the 5-inch supply. Excuse me. And we're tapping off of that supply. The secondary pumps are providing the pressure in order to overcome the resistance. And there's the terminal device. 300,000 BTUs, roughly 30 gallons per minute. The supply water temperature is 180 degrees. Return water is 160. Here's our control valve. And usually for larger units like this, 300,000 BTUs, that control valve is a modulating control valve. And then we also have a balancing valve over here. And the way we typically balance these systems is we open the control valve 100%. We set the pump at the design speed that we need. And then we manipulate these balancing valves to make sure that we have the right flow, in this case, 30 gallons per minute. And in this very oversimplified diagram, all of the terminal devices are the same size. And again, not for construction because there's a lot of components missing. Usually for this type of system, there would be an isolation valve perhaps here and here from the main, and that would allow you to shut those valves. Maybe they're ball valves or butterfly valves, whatever the right size is. And then you would shut that, isolate it so that you could service the terminal device. And you might also have let's say I always get, yeah, no, that's right. You might have a strainer so that as the fluid flows in this direction, it removes debris and material before it gets to the coil inside the terminal device and before it gets to the control valve. So that shows you some of the different components that you might have. And I also have, hopefully I didn't screw this up, I also have a detail of what you might consider for a terminal device. And again, in this case, we have two coils at 150,000 BTUs each, and you can see all the different piping components. In this configuration, they've shown a three-way valve. Here, you can use either a three-way valve or a two-way valve in your system. Most systems today use two-way valves to take advantage of the variation in the flow as the valves modulate open and close. We have a discussion, a separate discussion about how that stuff works in terms of control. Sometimes we will recommend that you put a minimum number of three-way valves on your terminal devices to ensure minimum flow, either required by the boiler if it's a primary variable flow system, or the pump if it's a primary secondary loop. So in this case, it would be a secondary loop. The secondary loop would have a minimum flow required by the pump, and we would select the number of three-way valves to equal the minimum flow required by the pump. So we've actually, I think, done pretty good on time. Do we have any questions out there, Brett?
Yeah, here's a great question, Rich. And maybe you can go back to your building for a second. Picture of the building. Yeah. So you know, when you start talking about designs, how do you figure out how many zones you're going to have?
That's a great question. So it depends on the type of system. Now I've shown in this case, implying that it potentially could be a fan coil system. And fan coils are generally maxed out at about approximately 60,000 BTUs, which translates into roughly 2,000 CFM. So a building this size, if it was using fan coils, let's say it was open floor design with just a furniture system. Now I know there's no such thing as a building that's 100% open plan with just a furniture system, no private offices, but we're going to exaggerate for a moment. So that means if I had 500,000 square feet and each terminal device could handle roughly 2,000 square feet, then I would need 250 fan coils for this building. The second category is if I created individual spaces within the building, such as conference rooms, they would tend to be on their own zone. And then we have other criteria, like if we have different exposures. For example, if we had a corner office, and a corner office would be have a northerly exposure and a westerly exposure, in which case, when we have two exposures, we typically put corner spaces on separate zones. So there's a whole series of the sort of discussions and decision-making process that we have to go through to determine how many zones that we're going to have in a building. And again, it depends on whether that's open office or private office, and specialty spaces like conference rooms, cafeterias, other types of private offices, corner offices, and so on.
Excellent answer. Can you go to one of your pictures of actually the detail piping, one of the detail ones showing the pumps? Yeah, scoop back one.
Yeah.
So there's a, well, it's a little hard to see. Good question here. Can you have the air and dirt separator and an expansion tank on the primary side of your pumping system?
Yes, you can. You could actually have, if you want, you could have the air and dirt separator on. You could have two in there if you want. Although in general, we only recommend one expansion tank because we only have one. We only want one point of no pressure change in the system. But you could have the air and dirt separator or the expansion tank on either the primary or secondary side. Generally speaking, we like to put the air and dirt separator on the secondary side because it sees the usually the majority of the flow most of the time. If you put it on the primary side and you put it, for example, in one of those three boilers, then only when that boiler is operational will you get the characteristics of the air separator, unless you put it in the common header, which for this discussion, the common header would be, even though diagrammatically it's very small, would have to go here, or it would have to go here, one of those two locations. That was a great question, Brett.
Yeah, I'm going to sneak one more question in. I like this question. Does the type of boiler, condensing versus standard, have an impact on your pipe selection?
That's a great question. In general, no. It doesn't really matter if it's condensing or non-condensing boiler. It should not affect the decision that you make on your piping material. The piping material is generally governed by temperature and pressure, and not by the type of boiler that's in the system.
Great question. Here's a comment, Rich. Each one of these slides needs a separate seminar. Thanks for putting this in 1 hour. So true.
Yeah, I mean,
true.
you can only cover so much material, and when you're trying to understand how the big picture pieces fit together, Yeah, this is kind of like the first step, and then you have to go into the boiler plant and the terminal system, the controls, and so on. It takes hours to go through all of this stuff. We have a couple of minutes. I'd like to show everyone before we leave, Brett, where you can download this stuff.
Yep.
So I'm just going to go to the TACO website. And under here where it says software, click on that. And click on, let's see, I want that, the load tool first. I think it's all on the same page. There it is. So we have the load tool, which is on the right. You can download this. You can just click on download, fill out a couple of things, and you can download the load tool for free. It's a great heating and cooling load calculation. And then the software that I use to create those diagrams, the HSS Hydronic System Solution, again, you download that for free, and it'll help you design any type of hydronic system. So it's a very, very powerful product. We have some other software packages here. FlowPro Design, that's specifically for residential systems. I personally, and I think it's safe to say that Brett and I don't dabble in the residential arena. You have to have a much more sophisticated set of skill sets to work in the residential. So it's a very highly directed discipline. So for those of us that have worked on the commercial side, I understand the basic principles of the hydronic systems on the rest of the residential side, but we really need to have guys like Dave Holdoff and Rick Mayo and John Barber give you guidance through that piece of it. And then the other tool that we have for software is called the Building Efficiency System Tool, abbreviated BEST, which helps you compare different HVAC systems. So that's all good stuff that you can download, and all of these are free. There's no cost.
All right, we've exceeded our time limit, my friend.
We've exceeded our time limit. So before I turn it over to Brett, I wanted to say thank you so much for allowing us to provide you with this training today. And be safe out there. I'm turning it over to Brett. Thanks a lot.
Rich, great job. Thank you so much. Really great. And David Johnston, I hope you're still on. Thank you for the write-up. Rich, he has informed, Dow Chemical recommends, and I can't read the whole thing, not to use galvanized steel is not recommended for use with ethylene glycol heat transfer fluids, even if they are inhibited, and especially if the temperature goes above 120. And there's a whole big reason for that. But David, thank you for filling us in on
Thanks,
that.
David. That was great. Yeah. I haven't really used galvanized in HVAC systems, so it's good to know.
It's not necessarily a good thing, or it can be a bad thing. So thank you, everybody. Again, email tomorrow. If you have some trouble getting those emails, send us some issues. And as with any email nowadays, if you don't get it, check your spam folder or whatever. So keep that in mind. A lot of thank yous, Rich. A lot of pats on the back. So thank you very much, everybody. And in 2 weeks from today, the next commercial one will be a little different focus. We are deep diving into FI and CI pumps. We're going to take them apart. Visually, unfortunately, I can't take them apart in front of you. But we're going to talk about everything there is to know about this product, a deep dive into the product itself. So bring your questions, and we'll cover that in a couple of weeks. So thanks, everybody. Stay safe out there. Signing off from TACO Land. Goodbye.